So now we are going to look at tutorial number 7, where you will see the applications of metrics in quantum mechanics. So in quantum mechanics, as I mentioned before, we have two kind of like simultaneous development in the earlier days, where you have the wave mechanics and you have matrix mechanics. So matrix mechanics are associated with the Heisenberg, right? So normally operators they are represented by square matrix, okay, whereas the vectors they are represented by column matrix. So in this case, you have two square matrices. You have H and you have A. Um, and I just want to mention, like, normally we reserve the capital H as the operator to represent the total energy of the system. So you can just view this H over here as the matrix representing the total energy of a system. And then you have another operator here, which is denoted by the matrix A. So there are four sets of questions, and this is rather commonly seen in your quantum mechanics course. So for those who haven't tried this, you might want to pause the video for a while and then you try it on your own before you look at the answers. Right, so now let's go to number 7a. So 7a here, they ask what are the eigenvalues of H. So to get the eigenvalues of H, this is very straightforward. If you remember that when you are given the square matrix and they ask you for the eigenvalues, the the first thing that you need to do is to diagonalize the matrix. So when you diagonalize the matrix, then you will have all the other elements equals to 0 except for the diagonal terms, right? So the diagonal terms will give you your eigenvalues. So in this case, H is already a diagonalized matrix, and your eigenvalues are 1, minus 1, minus 1. So in this case, you have a generosity of 2 for lambda, which is eigenvalue equals to -1. So what this means is that you will have two eigenvectors associated with this eigenvalue of -1. So we have done number 7a and we will go to 7b now. So here you want to find the eigenvector associated with each eigenvalue. So here you will use the usual method, the way you find the eigenvector in a normal case, where you have a non-degenerate case. You will apply uh, uh, the same approach that you learn in matrix. How do you find the eigenvector, right? So you will find the eigenvector for lambda equals to 1, and then you will apply the same method to find the eigenvector for lambda equals to -1. So in that case, you have two eigenvectors, and then you will use what we call as the Gram-Schmidt method to find the third eigenvector associated with this lambda equals to -1. So in that way, you will have three orthogonal eigenvectors, right? So let's look at this over the whiteboard. So now we want to find the eigenvectors for the three eigenvalues, right? So let us start with the eigenvalue lambda equals to 1. So if you write the matrix equation, here you have the matrix H over here multiplied by the column matrix, which represents the vector. Then you should get back the same column vector over here with the eigenvalue lambda equals to 1. Okay, so here we want to find what is A1, what is A2, and A3. So just for a note, the matrix H here, you have a H bar omega, which I have suppressed here. I did not include this because even if you include this, it will also appear on the right hand side and they will cancel. So now in order to solve this, you just have to multiply them. This matrix with this A1, A2, and A3, and you will have this on the left hand side to be compared with the right hand side. So now if you compare row by row, you will see that A1 is equals to A1. So therefore, if you bring A1, one of them to the other side, you will have A1 minus A1 equals to 0, and this is equals to 0. Okay, so A1 minus A1 is of course equals to 0. So this simply means that A1 is non-zero. in fact it is non-zero. So if it looks weird to you, you just have to imagine that a1, you can just give a number. So let's say a1 is equals to 3. So if I say 3 minus 3, this is exactly 0. But it doesn't mean that a1 is 0. Okay. Then if you go to the second row, you have minus a2 equals to a2. Again, you shift either one to the other side, and you have 2a2 equals to 0, and therefore a2 is equals to 0. And this applies as well to the a3. So a3 is equals to 0. So from this, you will have v1, which is equals to a1, 0, 0. But the a1 is an undetermined constant, so you can choose any value. So in this case, I choose a1 equals to 1. So this will be the eigenvector for my eigenvalue lambda equals to 1. Now we go to the second one, which is lambda equals to minus 1. We write again the same matrix equation, h multiplied by v equals to minus 1 v. So minus 1 is my eigenvector now. So I multiply the matrix, and I will have this on the left and the right. So now we compare row by row. You have a1 equals to minus a1, and this means that a1 is equals to 0. But on the other hand, the second row, minus a2 equals to minus a2, you shift another one. So a2 minus a2 is exactly 0, and this means that a2 is non-zero. Okay, so the same goes for a3. So in this case, the coefficients that I have not determined, that is that we do not know at the moment, is a2 and a3. But this one we can choose any values for this, so therefore I just choose a2 equals to 1 and a3 equals to 1. So now what happened is that we have the first set of eigenvector for lambda equals to minus 1. So we have v1, we have v2. So v1, v2 here, you can check that they are orthogonal. So if you take v1 dot v2, you will get equals to 0. So maybe I just also mention here. So since v1 is the column matrix, and so is v2. If you want to take a dot product in matrix, we just have to change either one of them into a row matrix. So here v1 dot v2 is going to be written as 1, 0, 0 multiplied by 0, 1, 1. So this is going to be 0, 0, 0. So this is exactly 0. So v1 dot v2 is equals to 0. It means v1 and v2, they are orthogonal to one another. Now we'll go to the third eigenvector, which is associated with the eigenvalue lambda equals to minus 1. So we have degeneracy of 2 for lambda equals to minus 1, and this means that there are two eigenvectors, right, for this eigenvalue. So how do we find them? So if we are not going to be too particular, right? If you are not going to be too particular, we can just choose any value of a2 and a3. So any value of a2 and a3, you will see that it should be a solution for the eigenvalue equation. Okay. But then now, if you normally we want to find the eigenvector which is orthogonal to one another. So here you have shown that v1 and v2 are in fact orthogonal to one another, and you want to choose v3 which is orthogonal to both of them. Okay, so that is where the Gram-Schmidt method comes in. But then if you do use the Gram-Schmidt method in this case, you will see that it will lead you to v equals to 0, 0, 0, which is your null vector. So in this case, the null vector is not the solution that we want, because if you put in a null vector over here, this is not going to be a solution for your eigenvalue equation. So fortunately, there is an easier way to solve this, right? So remember, let me recap. We want to find an eigenvector which is going to solve the eigenvalue equation. So basically, if you're going to put it back, it will give you eigenvalue lambda equals to minus 1. First thing. The second thing is that you want to find the eigenvector which is orthogonal to the first two, orthogonal to this guy and to this guy. Okay, and here, if you put let's say for example, if you put v3 equals to 0, minus 1, 1. So my a2 is equals to minus 1, a3 is equals to 1. So you take the matrix H over here multiply by this eigenvector, you will see that it will give you 0, 1, minus 1. So you can try this at home, multiply them, and this is what you will get. And you can take out the negative over here, so you have 0, minus 1, 1. So 0, minus 1, 1 is in fact the eigenvector that you put in on the left hand side, right? So therefore this shows that this V3 equals to 0, minus 1, 1 is a solution to your matrix equation or your eigenvalue equation. Okay, so that is the thing that we have done. And lastly, we want to make sure that this is in fact orthogonal, right? So here, what you need to do is you have to check V3 to be orthogonal to V2, and V3 is orthogonal to V1. So you can verify this at home, and you will see that this is in fact to be the case. So so that is how we get this eigenvectors for this matrix H, right? And again, the Lagrange method is basically something which we need to know, although we do not manage to apply it here, or we do not need to apply it here because there is an easier solution to this problem. But that could be something that you want to keep in mind in case you might need it for another kind of a problem, right? So let's go to the third question now. So now let's go to the question number 7C. So 7C here, they ask you whether the physical quantities represented by H and A can be measured simultaneously. So in this case, this is very easy to do because if you want to know whether these quantities can be measured simultaneously, it means the commutator of the two of them must be equal to 0. So it means that if you take H multiplied by A, this will give you the same answer if you take A multiplied by H. Okay, so HA is equals to AH. So this in quantum mechanics, this is very important because this represents the sequence of measurement. So if let's say you have HA, and HA, let's say you measure H first and then you measure A, and if you compare the results with AH, means you let's say you measure A first and then you measure H, so the sequence is reversed, right? So if they gives you the same answer, it means that before and after the measurements, the state are always the same. So therefore, that gives you the possibility of measuring these two at the same time. But for quantities, for example, the momentum and position operator, you will see that these two, the commutation are not going to be the same. So if you just imagine this is P and X, if you multiply P and X, it is not going to be the same as X multiplied by P. Right, so in this case, if you do this for these two case example here, you will see that these two commutes, right? So the answer for C is very easy. It means the answer is yes, because the commutator is equals to 0. So now we will go to the last question. They ask you to find the eigenvector that is common to H and A. So basically, you actually know the answer already because in C you have shown that H and A, they commute. So when they commute, it means they share the same eigenvector. Okay, so what I'm going to do next on the whiteboard is to show that the eigenvectors that we have found just now for H is in fact the eigenvector for A too. Okay, so let's work with the first one first. So the V1 is equals to 1, 0, 0, and the operator A is here, right? So let's say now I take operator A multiplied by V1, okay, and here you see that it will give you the same eigenvector as well. So here this shows you on the left hand side you have the V1, on the right hand side you have the V1, and therefore V1 is an eigenvector of A. What about the eigenvalue? So the eigenvalue here you see this is 1. Okay, so it means if my system is in a state of V1, so if initially my system is in V1, I do the measurement for A, I will get eigenvalue equals to 1. Sorry. Now, just to relate to what we have answered in C, if you measure right after you measure A, you got eigenvalue equals to 1, and you measure the second quantity, which is the H. It means now you're going to take the matrix H multiplied by this eigenvector. It will give you the eigenvalue equals to 1 as well. But at the end of these two exercises, right, at the end of these two measurements, the state of the system is always the same. So you start with 1, 0, 0. After the measurement, you will still get 1, 0, 0. So the system is not perturbed. Now let's go to the second one, which is the V2 equals to 0, 1, 1. Again, you just have to take the square matrix A multiplied by V2, and you will see that this is going to be equals to 0, 1, 1 again. So basically, you get back V2, and it means V2 is the eigenvector of A, and the eigenvalue in this case for A is 1 as well. V3 now, if you take V3A multiplied by V3, you will see that this is equals to 0, 1, minus 1. It looks weird, but then you can take out minus 1 over here. You can factorize out. So at the end, you have 0, minus 1, 1. So on the left-hand side, you have 0, minus 1, 1. And on the right-hand side, you also get the same eigenvector, except that in this case, my eigenvalue for this eigenvector V3 is equals to minus 1. Okay, so that is how you show that that these eigenvectors are in fact common for both A and H.